Have you ever wondered why casinos always seem to win in the long run, or why some video games keep you hooked for just one more try? The truth is, there's secret math at work behind the scenes. From the roulette wheel to the loot boxes in your favorite game, hidden probabilities and statistical principles are influencing outcomes and shaping our decisions. Today, we'll pull back the curtain on the math that powers games and gambling, and see how it can lead us into some pretty bad decisions if we're not careful. Don't worry, this isn't a dry lecture. It's a surprising, informal exploration of how understanding a bit of math can change the way you view chance, luck, and the choices you make. House Edge: Why the Casino Always Wins. Step into a casino, and you'll notice the bright lights, the exciting sounds, and the hopeful players. What you won't see is the mathematical advantage quietly working in favor of the house. Every casino game, whether it's roulette, blackjack, or slots, is designed with a built-in edge for the casino. In simple terms, the odds are rigged, just slightly, against you. For example, in American roulette, there are 38 pockets, 18 red, 18 black, and 2 green zeros. If you bet on red, you have an 18/38 chance to win, but the payout is 1-to-1, double your money, instead of the true fair payout of 1-to-1.111 that would account for the greens. This difference gives the house a 5.26% edge on that bet. In general, casino games provide a predictable long-term advantage to the casino, the house, while offering players the possibility of short-term wins. In the long run, that edge guarantees the casino profits. It might be pennies on each dollar bet, but across millions of bets, it's a fortune. Why can't a clever player just beat the game? Because these games are governed by probability, and no matter how lucky someone gets in the short run, the law of large numbers will eventually drag the results back to the house's advantage. As one witty headline put it, when a group of physicists visited Las Vegas, "Physicists in town, lowest casino take ever." The joke being that the only sure way to win was not to play at all. The harsh reality is that it's practically impossible for a gambler to win in the long term if they have no mathematical edge over the game. The house edge might be as low as 0.5% in a game like blackjack with perfect play, or as high as 25% in some lousy games like Keno. But as long as it's positive, the more you play, the more that edge grinds away at your wallet. It's been said that gambling is a tax on people who can't do math. And while that's a bit tongue-in-cheek, there's truth to it. To see how the house edge works, let's use a quick example. Imagine a simple game. You roll a 6-sided die and bet on a certain number. Say you bet on rolling a 6. The true odds of winning are 1 in 6. If fair payouts existed, a $1 bet would return $5 profit, because a win is that rare. But a casino might only pay, say, $4 profit on a win. This small payout gap means that for every dollar wagered, the casino keeps a few cents on average. Multiply that by thousands of bets per day, and you see why those casinos can afford the free drinks and lavish resorts. In essence, casinos make money by paying out a little less than true odds on each bet. You might hit a jackpot now and then, but mathematically, the longer you play, the more certain it becomes that the house comes out ahead. Historically, gamblers haven't always understood these principles, and that ignorance literally gave birth to probability theory. A famous story from 17th century France involves a nobleman and avid gambler, Chevalier de Mirage, who noticed his betting strategy wasn't working as expected. He would bet on dice games like trying to roll at least 1 6 in a few throws. He figured that if he increased the number of throws proportionally, he could also bet on getting at least 1 double 6 in a larger number of throws. Intuitively, it felt right, but reality disagreed, and he lost money. Puzzled by these unexpected losses, de Mirage turned to the mathematician Blaise Pascal for help. Pascal teamed up with Pierre de Fermat, and together in 1654, they essentially invented probability theory while solving de Mirage's gambling problems. They calculated, for example, that the chance of getting at least 1 6 in 4 rolls of a die is about 51.8%, a winning bet, but the chance of getting at least 1 double 6 in 24 rolls of 2 dice is only about 49.1%, a losing bet. De Mirage's mistake was assuming probabilities scale up linearly. The math proved him wrong, and it cost him. The resolution of this paradox, now known as de Mirage's problem, not only saved his pride, but also laid the groundwork for the entire field of probability. In other words, the casino was beating him before casinos even existed, thanks to the unforgiving logic of math. Gambler's fallacy, seeing patterns in the chaos. Even when we know the odds, our human brains have a hard time accepting what pure randomness looks like. We expect random events to even out in the short run, but that's not how probability works. This disconnect leads to one of the most infamous bad decisions in gambling, the gambler's fallacy. Simply put, the gambler's fallacy is the mistaken belief that past random events affect future ones. For example, if a fair coin lands heads 5 times in a row, many people feel like tails is due next. In reality, the chance of tails on the next flip is still 50%. The coin has no memory. The classic illustration of gambler's fallacy happened in Monte Carlo in 1913, a day that has gone down in casino lore. On August 18, 1913, at the Monte Carlo casino, the roulette wheel landed on black 26 times in a row. Think about that. The odds of 26 blacks in a row are astronomically low, about 1 in 67 million by one calculation. As the black streak stretched on, gamblers around the table went nuts, frantically betting more and more on red, because by their reasoning, red just had to appear next. It was overdue. But randomness doesn't have a schedule. The wheel doesn't know it just hit black 25 times already. So on the 27th spin, it came up black again, and again. People were losing fortunes doubling down on red, convinced each loss meant a bigger inevitable win next round. By the time a red number finally showed up, gamblers had lost millions of francs collectively, all because they fell for this Monte Carlo fallacy. The casino, of course, happily raked in those losses. This extreme event perfectly demonstrates the gambler's fallacy, thinking that a deviation in one direction, lots of blacks in a row, makes a deviation in the opposite direction more likely immediately. In truth, each spin was independent. No matter how many blacks had come up before, the chance of red on the next spin was still the normal roulette probability, 18/37ths on a European wheel, approximately 48.6%. There was never a cosmic force balancing the outcomes. The imbalance went on far longer than anyone imagined possible, because rare events do happen, and randomness can be very streaky. Why do our brains trick us like this? Psychologists point to something called the representativeness heuristic. Basically, we expect small samples of randomness to look representative of the larger pattern. If red and black are supposed to come up about equally, around 50-50 in roulette, then we feel like any short sequence should also be nicely mixed. So a run of 26 blacks feels impossibly wrong, as if nature must correct it. But mathematics says such streaks, while unlikely in any given stretch, are bound to occur if you play long enough. If you play millions of spins, a 1 in 67 million event eventually happens. The Monte Carlo incident is an extreme case, but smaller-scale gamblers' fallacies happen every day. The slot machine that hasn't paid out in a while, so it's due. The lottery numbers that haven't appeared lately, so they're due. Or even outside gambling, like thinking a sports team on a losing streak is due for a win. It's all flawed reasoning. Randomness has no memory. As one fallacy researcher quipped, the roulette ball has no shame. It doesn't care what happened before. The irony is, sometimes casinos exploit the gambler's fallacy. You might see signs on slot machines advertising that they just paid out a big jackpot. The implication, maybe now it's cold. Or conversely, some gamblers think a machine that hasn't paid in ages is primed to hit. Both ideas are wrong in a well-designed random game. Each play is independent, unless the game explicitly says otherwise. Some casinos will even display the last 20 roulette results on an electronic board, and you'll see players crowd around looking for patterns, like, oh wow, 8 of the last 10 were black, time to bet red big. The casino isn't doing this out of the goodness of their hearts. They know those boards encourage exactly the kind of faulty pattern hunting that makes people bet more. In reality, observing a random process shouldn't change your strategy, but it definitely changes people's behavior, and usually not for the better. Betting systems. Okay, so savvy gamblers might acknowledge that each spin or hand is independent. That leads to another idea. I can't predict when I'll win, but if I keep doubling my bet, I'll win eventually and then come out ahead. This is the logic behind the famous Martingale system, a betting strategy that sounds like a sure thing, until it financially ruins you. The Martingale is simple. Whenever you lose, double your next bet. In a game like roulette, say you bet $1 on red, and it loses. Next spin, you bet $2 on red. If that loses, bet $4 next, then $8, and so on. When you finally win, and you will win eventually if you can play infinitely, the win will cover all your accumulated losses and give you a profit equal to your original bet. It's a mathematical fact that if you had unlimited money and no betting limits, your chance of losing forever is essentially zero. Eventually, a win will happen. So victory, right? Wrong. The Martingale's fatal flaw is that real life is not infinite. You don't have unlimited funds, and casinos do have table limits. What the Martingale really creates is a high chance of a small win, but a small chance of a catastrophic loss. For example, if you start at $1, doubling each time, $1, $2, $4, $8, $16, $32. By the time you've lost 6 bets in a row, you've already bet and lost $1 plus 2 plus 4 plus 8 plus 16 plus 32 equals $63. And your next bet needs to be $64 to win back everything and net $1 profit. Losing 6 in a row on a roughly 50-50 bet isn't common, but it happens. In fact, it happens about 1 in 64 sequences on average, tilde 1.5%. If you had a bankroll of $127, you could withstand 7 losses in a row. But what if you hit 8 losses? The odds of 8 losses in a row are 1 in 256, approximately 0.4%. That's small, but not negligible. Play long enough, and it will come. And when it does, you'd need $256 for the next bet, and your total losses would be $255 by that point. You can see how quickly this escalates. The betting amounts grow exponentially. Eventually, either you reach a tables limit, or you simply go bankrupt trying to chase that one win. The Martingale is basically trading frequent small wins for the chance of one huge, devastating loss. If you graph out the expected value, it actually comes out net zero in an ideal 50-50 game, or net negative in a real casino game with house edge, because that tiny probability of disaster offsets all the little gains. As one author put it, it's a bad strategy for generating wealth when you're taking a small but non-zero chance of risking your livelihood for a puny dollar. The history books and casino ledgers are littered with people who tried Martingale or similar guaranteed win systems and eventually went bust. Even the famous Casanova, 18th century adventurer and ladies' man, wrote about using the Martingale and how it wiped him out when he hit an improbably long losing streak. The lesson? If someone claims to have a perfect betting system, be skeptical. If it sounds too good to be true, math will prove it is. The only nearly safe way to profit from a casino game is to have a positive expectation, an actual edge in your favor, which usually only happens if you're doing something the casino doesn't like. For instance, card counting in blackjack. A quick success story. Blackjack is one of the few games where skilled play can swing the odds slightly in the player's favor, if you can keep track of the cards. By counting cards, keeping a running tally of high and low cards seen, players can estimate when the remaining deck is rich in high cards, which favors them, and bet more at those times. This technique, popularized by teams like the MIT Blackjack team in the 1990s, can reduce the house edge and even turn it in the player's favor by a few percent. It's legal, in the sense that it's not cheating with a device, but if the casino catches on, they'll swiftly show you the door. Casinos have no obligation to let you play if you consistently win, and they don't take kindly to people using their brain to beat the game. In fact, many casinos now use multiple decks and automatic shuffling and trained dealers/pit bosses to spot counters. The cat-and-mouse game between advantage players and casinos is a whole story in itself. But for our purposes, the takeaway is, math can beat some games, but the casinos work hard to prevent it. For the average person, chasing losses or using betting progressions like Martingale is more likely to end in heartbreak than riches. The psychology of random rewards, why we get hooked. It's not just casinos that leverage the secret math of chance. Game designers, including video game developers, have learned how to use randomness to keep us engaged, even addicted. If you've ever played a video game where you grind for a rare item drop or open loot boxes hoping for a legendary prize, you've experienced this. The idea is that variable, unpredictable rewards are far more enticing than guaranteed ones. This was first studied by psychologist B.F. Skinner back in the 1950s. Skinner ran experiments with pigeons, giving them food rewards on different schedules. If a pigeon got a pellet every time it pecked a button, it would eat when hungry but not go crazy. If the pigeon had to peck a certain pattern or number of times, it would figure it out and do the work, a bit more enthusiastically since it's like solving a puzzle. But when the rewards were given on a random schedule, for example, on average 1 pellet per minute, but sometimes 3 pellets in a minute, then none for 5 minutes, and so on, the pigeons lost their little bird minds. They would peck compulsively, up to 5 times a second for 15 hours straight, frantically hoping each peck would be the one that pays out. In Skinner's words, variable interval is at the heart of all gambling devices. A pigeon can become a pathological gambler just as a person can. Sound familiar? Slot machines, with their random jackpots, are basically Skinner boxes for humans. Sometimes you win, most times you don't, but you never know which pull could be the big one, so you keep pulling. This principle has bled into video games as well. Many games use loot boxes or randomized loot drops, where, say, you have a 5% chance of a rare item each try. That uncertainty, maybe this next chest will have something amazing, creates excitement and drives players to keep playing or spending in-game currency. Game companies have literally hired psychologists to fine-tune these reward systems. They've found that the dopamine rush in our brains is highest when a reward is unexpected, or on a variable schedule. In other words, uncertainty is thrilling to us on a biological level. It's the same reason people compulsively check their phone notifications or refresh social media. Every so often, there's something really rewarding, a message from a friend, a bunch of likes, etc. And that possibility keeps us checking constantly. From a math perspective, these games often exploit the variable ratio schedule. You don't win every time, but after a random number of attempts. Interestingly, if you knew it was exactly every 10th try you'd get a reward, it would be less compelling. You might just wait or feel bored doing the other 9. But if it might happen on any try, this next attempt could be the lucky one. Casinos and game developers know this well. That's why slot machines sometimes string you along with small wins. They want to keep you in that zone of, I'm almost hitting it big, I feel it coming. And that's why a game like, say, Diablo or Genshin Impact uses random loot drops. The occasional amazing item drop out of the blue gives you a rush that keeps you slaying monsters or buying card packs. However, there's a dark side. Some people get truly addicted. The mechanism that keeps you engaged can also encourage bad decisions, like spending way more money or time than you intended. It's no coincidence that loot box systems in video games have been compared to gambling. In some countries, regulators have stepped in. For instance, in China, game companies are required to disclose the exact probabilities of loot box outcomes to players. Knowing the odds is a good first step, e.g., a 0.5% chance to get that ultra-rare item. But even when people know the odds, it's hard to truly internalize how slim a 0.5% chance is if you're emotionally invested. If you've ever caught yourself thinking, I've opened 50 boxes and didn't get the thing, I'm due for a hit soon, rewind to the gambler's fallacy we discussed. Unless the game explicitly increases your odds due to pity timers, you're not due. You could just be unlucky a bit longer. Interestingly, some game developers have realized that true randomness can actually feel too cruel for players' tastes. Humans expect randomness to be fair in the short term. Remember representativeness. So when a game is 95% likely to succeed at something and you fail 3 times in a row, you feel absolutely robbed. You might rage quit, thinking the game is cheating, even if those outcomes were legitimately random. To prevent this, designers sometimes fudge the numbers in the player's favor. Shh, don't tell. For example, the strategy game XCOM faced player ire because a 90% chance to hit could still miss, and sometimes you'd miss several high-chance shots in a row. Some players swore the game was lying about the odds. In response, the developers revealed they use a system to subtly boost the player's odds after consecutive misses. They implemented what is essentially a pseudo-random luck compensator. If you miss a lot, the game quietly increases your future hit chances to avoid long, unlucky streaks. Another example, legendary game designer Sid Meier of Civilization fame once adjusted his game's combat system after playtesting. He found that if a battle was said to have a 33% chance of victory and a player lost 3 times in a row, they'd be furious. So he changed it such that if you lost twice at 33%, the game would guarantee you win on the 3rd try. In effect, the game was no longer truly random. It was engineered to feel random enough while matching players' psychological expectations. Similarly, the developers of Fire Emblem, a tactical RPG series, discovered that players hated occasional bad streaks and hit percentages, so they started using 2 random rolls instead of 1 and averaging them. This skewed the results such that a displayed 80% chance to hit would actually hit around 92% of the time, making results more in line with what players feel 80% should be, i.e., very likely. These tricks keep players happy and engaged, but they also teach an interesting lesson. Our intuitive sense of probability is so flawed that game makers often bend the real math to meet our expectations. So next time a game seems rigged, it might be rigged in your favor to protect your feelings, or it might indeed be rigged against you to pad the company's pockets. The common thread is, math is behind it all. Whether it's pure probability or massaging the odds, the numbers dictate the experience. When intuition betrays us, the Monty Hall dilemma. No discussion of math versus bad decisions would be complete without the legendary Monty Hall problem, a brain teaser from a game show that famously fooled thousands, including PhD mathematicians. It's not directly about gambling, but it is about making a decision under uncertainty, and it perfectly illustrates how counterintuitive probability can be. The scenario: you're on a game show with 3 doors. Behind one door is a new car, the prize. Behind the other 2 doors are goats, booby prizes. You pick one door, say door number 1. The host, who knows where the car is, then opens one of the other doors, revealing a goat. Now 2 doors remain, the one you picked initially and one other unopened door. The host offers you a choice. Stick with your original door or switch to the other unopened door. What should you do to have the best chance of winning the car? Most people have a gut reaction. It doesn't matter. There are 2 doors left, so it's 50-50 now. Might as well stick with my first choice. That gut reaction is wrong. The mathematically correct move is to switch doors, which gives you a 2/3, about 66.7%, chance of winning, versus only 1/3, 33.3%, if you stay. How can switching be twice as good? Explaining it in words: when you picked your initial door, there was a 1/3 chance you picked the car and a 2/3 chance you picked a goat. Those odds don't change after Monty, the host, opens a door. Crucially, Monty's action of revealing a goat gives you information. If your initial pick was a goat, 2/3 chance, the remaining unopened door must have the car. If your initial pick was the car, 1/3 chance, then the other door is a goat. By switching, you'll win in all the cases where your first pick was wrong, which is 2/3 of the time. Only if you were right initially, 1/3 chance, will switching hurt you, so you double your chances by switching. This result is so counterintuitive that when it was publicized in Marilyn Vos Savant's Ask Marilyn magazine column in 1990, it caused an uproar. Thousands of readers wrote in to say she was wrong, including almost 1,000 PhDs who seemingly couldn't believe it. Even when given explanations and even computer simulations proving the solution, many folks refused to accept that switching was better. It just felt like it should be 50-50. The great mathematician Paul Erdos didn't believe the solution until he saw a simulation with his own eyes. The Monty Hall problem is a potent example of how our intuition can lead us astray in probability and decision-making. It's essentially a paradox where the correct answer seems absurd. Hence, it's called a veridical paradox. The solution is true but unbelievable. If you've never heard it before, it might melt your brain a little. If you have heard it, you know how satisfying it is once it clicks. Either way, it teaches a valuable lesson. Sometimes the best decision in a game or in life is the non-obvious one, and you might need math to see why. Monty Hall's lesson extends beyond the game show. It encourages us to question our assumptions and examine the information we have. How often do we stubbornly stick with a choice because it feels equal either way, when in fact there's new information we haven't properly accounted for? There are other famous paradoxes in puzzles like the birthday paradox or the Monty Hall's evil twin, the 3 prisoners problem. But the key point is that our brains didn't evolve to do probability calculations intuitively. They often mislead us, whether we're gambling, gaming, or making everyday decisions under uncertainty. Understanding the secret math can save us from those pitfalls. Conclusion: playing smart. Games and gambling can be a lot of fun. The uncertainty, the risk, the occasional reward all fire up excitement in our brains. But as we've seen, there's always math in the background. Whether it's the casino's house edge ensuring profit over time, or a cognitive bias leading you to see patterns in pure randomness, or a video game drop rate keeping you grinding for loot, knowing the numbers can help you make better choices, or at least understand the choices you're making. We uncovered how casinos bank on probability, literally, to ensure that, on average, they win and you lose. We saw how even brilliant people can fall prey to the gambler's fallacy, or a tricky probability puzzle like Monty Hall. We looked at how game designers use random rewards to keep us engaged, and sometimes even cheat randomness to meet our expectations. The thread through all of this is that math is an incredibly powerful tool for understanding risk and reward. When you peek behind the curtain, some things that seemed mysterious or unfair start to make sense, even if they remain unfair. So next time you're at a casino, you'll know that every spin of the wheel or toss of the dice isn't just governed by Lady Luck. It's governed by cold, hard probabilities. Next time you play a game, you might have a new appreciation for the balancing act designers do with randomness. And next time you find yourself saying, "I have a feeling this will happen," you might pause and recall what the numbers say. Ultimately, knowing the secret math behind games and gambling doesn't ruin the fun. In a way, it can make it more interesting. You can still enjoy the suspense of a roulette spin or a loot box opening, but you'll do so with eyes open, aware of the realities behind the scenes. And if you ever decide to gamble, you'll set limits and avoid chasing losses, because you know how that movie ends. As the old gamblers, saying goes, the house always wins, but the informed player at least knows why. Stay curious, play smart, and may the odds be ever in your favor, just don't trust them blindly. Thanks for watching. Your turn. Which part was the most surprising? The house edge, the gambler's fallacy, or Monty Hall? Drop a comment below, and I'll see you in the next video.